Alright, we'll work through three examples, kind of three different scenarios, one in terms of x, one in terms of y, and then one revolving around something that's not one of the axes. Alright, so in this first example here we've got find the volume of the solid generated by revolving the region bounded by y equals x squared and the x-axis on the interval from -2 to 3 about the x-axis. Alright, so I would highly recommend sketching this out so that you know what you are looking at here. So that's what I'm going to do first. We're going to sketch. Alright, important parts in this. They gave me the curve, y equals x squared. It's bounded by that curve, and it's bounded by the x-axis, and it's bounded on that interval from -2 to 3. Alright, and the other important part is here, you've got to know which axis you're going around. So we're going about the x-axis. Alright, so I'm going to go ahead and indicate that so I don't forget that we're going around my x-axis right there. Alright, this curve, x squared, it's going to go through the vertex, and it's just a nice little parabola. So I don't have to be really accurate when I draw this at all. Okay. Now it's bounded between the x-axis, and I'm going from -2 to 3. So let's say -2 is right there. 3, let's say 3 is right there. Okay, so the region that I am focused on is going to be in here and then in here. Alright, now let's go ahead and place that representative rectangle on there. I'm revolving around the x-axis, and here's my curve that I'm working with. I know it's got to touch the axis of revolution and go up to my curve. Alright, so kind of wide there, but we get the idea. Alright, there's my representative rectangle. Alright, in other words, that is the radius of the disk. So the distance from here to here, that's going to be my radius of my disk, f of x. Okay. Okay. Now let's set up our definite integral. Alright, let's use our formula. So the first thing I'm going to do is write down the formula from the other page. It was v equals pi times the integral from a to b of f of x squared dx. Alright, and if you want to think of this f of x being the radius, you can do that. Okay, the radius squared, the distance from the x-axis up to f of x. Okay, so as I begin to work this out, it's going to be pi times the integral of a to b. Alright, so -2 to 3, because it's got to come off my x-axis. Everything's in terms of x here. Alright, my function is x squared, so x squared, and the formula says to square that distance, and then dx. Okay, at that point, once you have the setup and everything's in there according to the formula, then this is just straight integration that it probably at this point you have been doing a long time. Simplify, integrate, and plug in your things. So we'll go ahead and work this one out. We may not work out the ones examples in the future, but we'll do this one. Pi times the integral from -2 to 3. Let's turn that into an x to the 4th dx. Alright, now if I integrate this, I'm going to have pi on the outside times a 1/5 x to the 5th, and I'll be integrating that from -2 to 3. Alright, plugging in the 3, we'll have 243 over 5, and then minus, plugging in a negative, that's going to give me a negative value, -32 over 5, and going ahead and plus and switching that out, I should end up with a 55 pi. Alright, usually I have my students leave things in terms of pi like that, so I've got a nice little 55 pi there. Alright, so that one pretty much was a straightforward example. Everything in terms of x, I was revolving around that x-axis. Okay, now let's do a second example. This time let's put the curve revolving around the y-axis. Okay, in this example, find the volume of the solid generated by revolving about the y-axis. The region in the first quadrant bounded by y equals x squared, the y-axis, and the line y equals 6. Okay, so let's go through there and find all of our important parts. We're still using this y equals x squared, but this time I'm going to be bounded by the y-axis and the line y equals 6. Alright, so I'm going to start by sketching. Okay, so I still have that parabola, but I only want in the first quadrant. It did say only in the first quadrant, so I only need to be focused here. Let's go ahead and label this y equals x squared. Okay, I am revolving around the y-axis. So let's put that on there so we don't forget. Okay, and then let's add that line y equals 6 on there. So let's just say if I come up there to 6. So if I add that, that's y equals 6. Alright, so I'm bounded by the y-axis, y equals 6 in this curve, so that means I'm focused on this area right in here. Alright, now let's put the representative rectangle on. Alright, I'm going to be revolving around the y-axis. Alright, so that means my representative rectangle has to touch my y-axis. So, representative rectangle. Alright, now, how wide that is, that's going to be a delta y. Okay, and you can think of this as being the radius of that disk, because as I revolve around that y-axis, this right here, the distance there, will be the radius of my disk, f of y. Okay, now something that you might want to consider here, we know we're revolving around our y-axis and everything. Our limits of integration have to come from this y-axis, and the other thing that you have to note, this equation is written in terms of x. We need to solve it for y because I've got to have everything in terms of y. If I'm going to go, my limits of integration are going to be from 0 to 6. Alright, that's off my y-axis. I'm revolving around this. My delta y is how wide that representative rectangle is. I've got to solve that equation for y. Okay, so let's go ahead and do that. Let's solve for y. Okay, so that's what I'm going to do. So I'm going to start out with y equals x squared. I'm going to take square root of both sides. Square root of y equals x. So in other words, I'm just going to go x equals square root of y. So this is that curve in terms of y now, which is what I need. Okay, so now let's set up our formula for our definite integral. Okay, so this one, v equals, it's still going to be pi times the integral from a to b. This time it'll be f of y because everything is in terms of y, that quantity squared, and then I'll have a dy at the end there. Alright, so for this particular one, v equals pi times the integral. Alright, we're going here's 0 and here's 6. We were up to 6, so from 0 to 6. Alright, the function in terms of y will be square root of y squared and then a dy. Alright, now at this point, like I said, you should be really proficient at integrating a definite integral and all that kind of stuff, so I don't want to take the time to do that in the video. You could pause the video, go ahead and work that out, and I do believe the answer should be 18 pi if you do that. So you could pause the video, work it out, and see if you can actually get 18 pi on that. Alright, now for the last example. Alright, in this last example, we're going to revolve around a line that is not an axis. That's a pretty common thing that happens a lot. They start you out revolving around either the x or the y-axis, and then they start taking you away from that. So in this example, it tells us to find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. Okay, so again, I'm going to want to draw a sketch of this so that I know what's going on. Okay, that's going to be an upside down parabola, and I've got y equals 1, so I'm going to need kind of a lot of room here. Alright, so let's take a look at important parts here. Okay, so f of x equals 2 minus x squared. Alright, and then I've got a g of x equals 1, and then about the line y equals 1. Alright, so I'm going to put this one on first. I know that it's shifted up 2, and it's going to be an upside down parabola, so I'm going to make that pretty high so I've got room to work here. Let's say this is 1, let's say that's 2. Okay, so there is my f of x equals 2 minus x squared. Alright, my g of x equals 1. Okay, we said this was 1 because we said that was 2. This is 1. So my line, y equals 1. So this is g of x equals 1. Alright, but I'm also revolving around this y equals 1, so it really doesn't make any difference there. Alright, now I'm going to be revolving around that. So I'm going to put my little arrow on there to remind myself which way I'm going here. Alright, now if it's bounded by those two curves, that means I'm focusing on this area right in here. Okay, and my representative rectangle then is going to touch my axis of revolution and my curve, and everything is in terms of x here, so we're good. So there's going to be my representative rectangle. It'll have a delta x, how wide it is this way. Alright, and then keeping in mind that again it's still going to be my radius. This distance will be my radius of my disk, because it'll revolve right around that, so my disk will be up there. Okay, and then we have additional things that we've got to find on this one. Okay, I don't know what that point is, and I don't know what that point is right there, but I'm going to have to do that for my limits of integration. So those are my points of intersection. I'm going to have to find my points of intersection. Alright, so let's see if we can squeeze that on right here. Points of intersection. Alright, that should be something that you should be able to do relatively easy. Hopefully you remember that all you have to do is set the two curves equal to each other. So 2 minus x squared, and I'm going to set that equal to 1. So I'm going to set those two curves equal to each other and then solve. So 2 minus x squared equals 1. Let's see, subtract 1 from both sides. So, and then move that x over to make it positive. Probably that'd be good. 1 equals x squared. So x is equal to plus or minus 1. Okay, so this has got to be negative 1. This over here has got to be 1. Okay, so for those 2 points right there. Alright, now to get the distance of this radius, alright, this radius of my disk here, I got to get this distance. Okay, you're going to have to plug a number into f of x, because if I plug a number into f of x, that's going to give me the distance from here all the way up to the f of x curve. Alright, but that's too much. I don't need this right here, so then if I subtract whatever I would get when I plug a number into g of x, if I subtract this distance, so I've got this entire distance, which is my top curve, alright, minus the distance to the bottom curve. Alright, that would leave me with what is left right there. Okay, so let's put that in there. I'm going to run out of room here. So calculating my, let's do it in red, calculating my radius of my disk. I need to take the distance to the top curve minus the distance from the bottom curve. Alright, so I'm going to go top curve. I'm just going to write it that way, top curve minus bottom curve. Alright, my top curve is my f of x, because that's the parabola. The bottom curve is the g of x curve. Alright, so my f of x curve was 2 minus x squared, alright, minus my g of x curve is 1. Okay, so subtracting right there, I'm going to have a 1 minus x squared. Alright, so that right there is my radius, the distance of my radius, of my disk. The distance from here to here. Alright, now I think I'm finally ready to set up my formula for finding the volume of this. Okay, so my formula, V equals, and I'm going to kind of rewrite the little formula here to instill what we did here. It's going to be pi times the integral from a to b. Alright, what did we do? Well, we found the radius of that disk, and we found it by doing f of x minus g of x. Alright, now you don't necessarily want to memorize the quantity squared dx. You don't want to memorize f of x and g of x, because if they change the function names, alright, so it might be better for you to actually put in there top curve minus bottom curve. But you subtract the two curves there, that'll give you the distance of that radius, and then you square it. Alright, so pi times the integral, we found our points of intersection, alright, as -1 and 1. Alright, we did this already, we did the math right here, so the radius is going to be 1 minus x squared. I have to then square that quantity, dx. Okay, and then again here, hopefully you can calculate this integral out with too much problems. Probably what I would first do before I try to integrate this is I might FOIL it. So let's go ahead and do the FOIL step for you. Volume equals pi times the integral of -1 to 1. If we FOIL that out, we'd have a 1 minus a 2x squared plus an x to the 4th, and then dx. Alright, so foiling that out. From there, you should then be able to continue. You can hit pause on the video and then try to integrate that. Alright, if you do that and you get done, you should have a 16 over 15 pi as your final answer. Okay. Alright, so in this first one right here, let's say that they are asking us to find the volume of the solid generated by revolving the region bounded by y equals x squared plus 2 and y equals x plus 4 about the x-axis. Alright, so the first thing I'm going to do is I'm going to do a rough sketch so that we can visualize and see what we're working with here. Okay, so upright parabola and line, so we probably only need first and second quadrants here. We'll make our picture kind of big. That would be good enough there. Okay, so upright parabola shifted up 2. So really rough sketch there. Y equals x squared plus 2. Alright, and slope of 1 up 4 on this line. So goes through there and maybe has a slope of 1. So let's just generically say right there, y equals x plus 4. Okay, so the region that I will be revolving around that x-axis right there is inside, right in here. Alright, first off, I know I'm going to need to locate those 2 points of intersection, because I'm going to need to run this along my x-axis from A to B. Alright, so I've got to find those intersection points. So finding those intersection points, you're going to set the 2 curves equal to each other. So points of intersection. So I'm going to take the x squared plus 2 and set that equal to the x plus 4. Alright, looks like I'm going to have a nice little parabola here. If I move everything to the left, I'd have an x squared minus an x minus a 2. This is going to factor pretty easy into an x plus 1 and an x minus 2. Alright, so that's giving me an x equals -1 and an x equals 2. Alright, so this intersection point is -1, this intersection point is 2. Alright, now let's see. Let's make sure we're going to have washer method here involved. I'm revolving around the x-axis. There's my region. If I make my representative rectangle perpendicular to that axis of revolution, that would be my delta x right there. When I revolve that around, there's that gap right there. So you can clearly see that that would be the washer that would be formed when I do this. So now I can go ahead and set up my washer formula here. Let's generically do it without plugging anything in first. Alright, so the volume would be pi times the integral from a to b. Alright, now I'm going to use top curve and bottom curve here. So top curve squared minus bottom curve squared. And then dx, because everything is in terms of x. Okay, but like I said, depending on your professor, this could be outside radius squared minus inside radius squared. Okay, so my top curve is my line, so that's going to be the x plus 4. So replacing here my values, pi times the integral of -1 to 2, top curve, x plus 4, quantity squared, minus that bottom curve. The bottom curve is the parabola, so x squared plus 2 squared, and then dx. Okay, now at this point, I'm not going to work out the integration here, because if you're doing washer method and volume method in calculus, you know how to do the integration. Foil that out. You can do it longhand. You can also use your calculator as well and get that answer. If you would want to stop and work it out by hand to see if you get the right answer, I believe it's 162/5 pi when left in terms of pi. So if you do have to work it out by hand, I'd probably pause the video, work it out, and see if I could come up with that. Otherwise, then you should be good here, because the main thing is, can you plug everything into the washer formula correctly? Alright, can you find those points of intersection, and can you determine that, yes, by sure it is a washer method problem? Okay. Alright, now let's do a second example. Alright, the second example will be a little more involved because of what we're going to revolve around. So in this example it says, find the volume of the solid formed by revolving the region bounded by the graphs of y equals square root of x minus 1 and y equals x minus 1 quantity squared about the y-axis. Okay, so again, these equations are in terms of x, but I'm going around the y-axis. Okay, so that means I'm probably going to need to, if I plan on using washer, I'm going to need to convert these into equations in terms of y. But let's start with our sketch. First, let's see, okay, square root and parabola here, it's going to still be in the first quadrant primarily. Okay, so square root function, this one's going to be shifted 1 to the right, and square root is up to the right. Let's just do that for y equals square root of x minus 1. This will be a parabola. It's going to also be shifted 1 to the right, upright parabola. Alright, I'm not really concerned with this part of it. We'll go ahead and put it on there just so you can see it is a parabola with a vertex at 1. And there is the y equals x minus 1 quantity squared. Okay, so my region that's bounded by those two curves are right in there, and I'm revolving around the y-axis. Alright, so if I need to use, if I'm intending to use washer here, this is my axis of revolution. That means my representative rectangle would have to be perpendicular to that y-axis. So that representative rectangle would be right there, and it would be delta y. Alright, I know my intersection point here is at 0. I need to find this intersection point on the y-axis. So I again have to find intersection points, but I cannot right now, I cannot set these two curves equal to each other, because if I set these two curves equal to each other, I would be finding the value of x, so I would be finding this point down here. So the very first thing I need to do is take these two equations and rewrite them in terms of y. So I think I'll do that in blue. So let's write that down here. Let's rewrite equations in terms of y. Alright, so let's just take this top parabola right here. Y equals x minus 1 quantity squared. Alright, so let's take the square root of both sides to get rid of that 2. So I'd have square root of y equals x minus 1. I can add 1 to both sides. So square root of y plus 1 equals x. Alright, so the parabola, when rewritten in terms of y, is this equation right here. And then let's do the second one. y equals square root of x minus 1. Alright, since I've got square root right there, let's square both sides of the equation to get rid of that. So then I'd have a y squared equals x minus 1. And again, add 1 to both sides. So y squared plus 1 equals x. Alright, so there is the square root function rewritten in terms of y. Okay, so now I have these rewritten in terms of y. So to find that intersection point on the y-axis, I can set these two equations equal to each other and then solve for y.